Okay, by the way, hi Logia. Uh, this is not for the attendance. This is for a makeup exam, so you don't need to scan the QR code. And also, I need your schedule. Uh, okay, so okay, you can scan to decide whether you want to join the makeup exam or not. Okay. Okay. Uh, so as I mentioned as early, I will go just around 30 minutes for a lecture, continue the chapter 6 a little bit, and then take sometimes maybe 5 minutes break, and then we have a quiz. Okay. Okay, I will give you another link if you maybe decide later. You're still not sure today. I will give you another link in the Moodle. Okay. So let's just continue chapter 6. Okay. Just a little bit. Okay. So what we have learned, okay, what we have learned from chapter 6, first is the area uh, between curves. Okay. And now we will focus on the volume. Okay. Now in volume, the difference is you have a solid product. Okay. You have a solid product. And to imagine how the solid is appear, they are coming from, if you have a curve like this, and you rotate the curve. Okay, you rotate the curve. So imagine it's rotated like this. Okay, so it's like imagine like it. Maybe you buy a bread that shape. Okay, so imagine that this is coming from the curve, and you rotate them. Okay? You rotate the bread. Okay, you rotate the curve, and it becomes like a bread like this. Okay. Okay. Now, if you have a solid like this, okay, to uh, to derive how it coming from how it's coming from the curve and then rotate, the first thing we need to do is we slice them. Okay, we slice. Okay, we cut. Okay, we cut. We cut. We cut. Okay. And you see that maybe we have like this uh, uh, cross section area. Okay, if we cut this solid product. So this is a random solid product. It doesn't need to be really circular, but it's like have a random shape. Okay. And let's say it is uh, on a plane X plane. Okay. All right. And let's name this cross section A. Okay? A of X, a function. Okay. And if we uh, take the same approach as we did before, we slice with some thickness. Okay, with some thickness. Okay, let's say our thickness is we call it the delta. Okay? We call it delta x, and we have a sample points, and we put the sample points. Okay, xi, a sample point there. Now to approach on how the volume is, we need to remember certain geometry, a certain geometry. For example, the easy one that maybe you can remember, maybe a circle like this and having this. Okay. Okay. The volume of this tube. Okay. This is area multiplied with the height, right? Okay. So this is the area. This is the height. Okay. So the volume here is the area multiplied by height. Okay. Generally speaking, if we look back into the volume here, if you want to calculate the volume of this piece, one piece here, area multiplied the height. The height is we taking this in the delta x. Okay. So that means our volume here, we can volume of one piece is the a of x multiplied with the delta x. Okay. And this is depends on the sample points. Okay. Now we have the volume for just one sample. Okay. Now if you have more than one, like this shape here, we have some n 1, 2, 3, 4, 5, 6. We have seven samples. Okay. Now the idea becomes we need to have the sigma of all the area with the xi sample and multiply with the delta x. And this will be depends on how many and if the number of the rectangles or number of the small volume increasing, this will give you an idea of a limit as it's getting large. Okay, and the rest of it, when we are looking here, we need to link or connect with the previous understanding or previous definition of the sum and integral. That is, if we have a solid, and this is a definition of the volume in our integral, if you have an S, any solid random product that is between A and B, okay, if you look at the previous shape, and if the cross section of that S is in the plane px, okay, you cut in plane px, okay, which means you have an x-axis here. If you cut this, we call this plane is plane x, okay, and it's perpendicular to the x-axis. The cross section is A, where A we define the A is a continuous function. The volume will be the limit as n approaching infinity, sum from 1 to n, a x sample delta x, and we can convert this into integral from a to b, a of x dx. Okay. Okay. Now that is definition of the volume of our integral. Okay. Okay. Now to have more understanding, let me show you an example on how we can use this definition here. We can use this definition, okay, the integral here into some applications. Okay, let me give you the idea of. Let me draw you a sphere. Okay, let me draw you a sphere. Okay, let's say this is a sphere. Okay, and we have this is the radius is r. Okay, the radius is r. So let me draw the radius here. Okay. Okay. Now, if you remember, the volume is the for sphere. Okay, the volume sphere is 4/3 pi r cubed, right? The volume of sphere. Okay. Now imagine we are going to do the same thing as we did with the example before. We cut the sphere. Okay, we cut the sphere. Let's say we cut here. We cut here. We cut in this. Uh, this. Let me make the line first. Let me make the line. So this is the cut. Okay. Okay. And from here, I will get the cross section. Okay, let's say the cross section is this one. Okay, this is the cross section. So you have a circle here. Okay, and when you have a ball, you cut the ball, and you have a circle.
So imagine you are cutting the sphere into a circle cross sections. So you cut and take the the radius of that sphere to be y. Okay, that will be the radius of a sphere. And then in this x-axis, let's say we have x. Okay, that the point that we are cutting the sphere through. Okay, so we cut the sphere through the point of x, and then we have radius y in the circle. Okay. Okay, and we can have this triangle relation between x, y, and r. We can use the Pythagorean theorem to rewrite the y squared become r squared minus x squared, or we can rewrite y equals square root of r squared minus x squared. Now this is the equations that we want to follow because we want to have the functions of x. So we are going to exchange all into function of x. So we can write the area of x. Okay, so we can write the area. Okay, let me move to the right, and if we looking at the circle, okay, this is just to confirm that our circle has a radius y. Okay, so we can write this radius y into our area, so pi y squared. Okay, and then because area in this equation will be a function of x, then we can exchange y into r squared minus x squared. Remember that the radius here is a constant. Okay, so we can rewrite the area becomes these equations, and then we can compute the volume of our sphere. Okay, all right, now we can compute the integral from negative r, okay, from the left side. Okay, so that will be the first endpoint, our a, negative r, until r or b. Okay, so if we remember, or if we are looking back into the how the volume is stacked up. Okay, it's like the slicing of our sphere. Okay, with the first slice, or the one slice of the disk will be having a thickness of the x. Okay, and the radius of y, and then we are going to add all those slices. Okay, we add all those slices, then we can define those summations become integral from negative r to r of area multiplied by dx, and an area in this case is a function of x. Okay, we already defined on the top equations. So we can also imagine the volume of sphere. Okay, instead evaluating from negative r to r, we can also use the symmetrical property of the sphere, then we can just evaluate from 0 to r and then multiply by 2. Okay. Okay, let me move to the left and let's write the pi because it's a constant, so we can factorize outside and we can rewrite the information r squared minus x squared and then dx. And we can integrate the r squared become r squared x because r is a constant. Okay? R is constant, so we just integrate as a constant, so we can multiply with x, and then negative x cubed over 3, and then evaluate from 0 to r. Okay, then the final results will be we can just evaluating the 0 to r inside the equations. So r cubed minus r cubed over 3. Okay, let's compute this. So r cubed minus 1 over 3 r cubed become 2 over 3, and then we just multiply with 2 pi, and then it became 4 over 3 pi r cubed. And this is the volume of sphere that we already know, and we can derive this formula from our definition of integral. So you can use the integral to find some certain formula on some geometric formula that you know, and we can have this idea on how this is built up from. This is built up from the disk. Okay, so if you remember the circular cross section in the sphere that is on the left side of the picture here. So this is the important thing. Okay, this is the important thing in all this integrations method. Okay, so we need to imagine that we have a circular cross sections. Okay, and that is like a disk. Okay, we just multiply the area and multiply with the height, which is the dx. Okay, in our case. Okay. Okay, let's say we have an example of a simple curve. Okay, let's draw the curve. Okay, let's say the curve is probably looking like this. Okay, maybe let's say we have a simple function here, maybe square root of x. Okay, so y equals square root of x. That is our curve. Okay, so imagine this curve. Okay, this curve. Maybe we can evaluate from 0 to some constant. Okay, and then imagine the curve will be rotating through the x-axis. Okay, you can imagine the curve rotated, and this is how it looks like. The shape, it's like a face, right? Face for maybe for plants, right? It's similar shape, but it's regardless, when we are rotating this curve, okay, we are going to have the circle that is similar to what we have done in the sphere formula previously, and we have the disk, okay, with the dx as the height, and then the radius is the y. Okay, so we have this similar method. Okay, or the same method here using the disk. Okay? The disk shape. Okay, so we can just evaluate, multiply the area, which is pi the radius squared, which is the radius is the y, or in our case here, because we are evaluating it with respect to the x, we are going to have a function of x, okay, for the area also. Okay, and for example, we evaluating the volume from let's say constant from 0 to some maybe 3, and then we write the formula pi, and then the radius. What is the radius now? We are having the radius is square root of x. That is our y, right? And we need to write it in the function of x. So we have to write in x, and that is our formula, and we can compute, and we know the results, right? Okay. Okay, in another example, we can also, let's say we draw a curve like this. Maybe this is curve x squared, or maybe any even functions. Okay, and we have the circular or the disk in the middle here, and we rotate through the y-axis, and we have now the difference will be, it's not the x but dy. Okay, so we are evaluating the disk with the radius is x and the height is dy. So the radius is x. Okay, let me write. So we can write the functions as a function of y. So the left one, let's say it's function of x, the right one is the function of y, and we can evaluate with both method. Okay, it depends on how the curves, and it depends on the case also which rotations the curve will be. Okay, that is the summary of, we call the method usually called a disk method. Okay, the disk method. Okay. Okay, let me go through some example to give you more understanding in this method. Okay, let's say we have uh, the region. Okay, let's say the region R bounded by curves y equal x and y equal x squared. Okay, and the region is rotated about the x-axis. Okay, that's the question. Okay, find the volume. Okay, of the resulting rotation or resulting solids. Okay, so the solid is created by rotating the region R. Okay, and that is the boundary curve, the curve y equal x and y equal x squared. Okay. Okay, let me go through the curves itself. Okay, let me draw. Okay, this is the y equal x. Okay, the blue, light blue. Okay, let me draw the other one. Let me select the color. Okay, let's check the proportions. Okay, I think it's too small. All right, too small, and I don't think we can observe with that small area. Okay, let make it a little bigger. Okay, this probably the curve. Okay, okay, let's say that is the curve. It's still small, but I think it's better compared with the previous one. Okay, let's just say this is the curves. Okay, so y equal x and y equal x squared. The green one is y equal x squared. So this is the R. Okay, between the curves, between two curves, we have R. Okay, okay, yeah, it's y equal x squared. Now we need to rotate. Okay, rotate is a region, and this is the rotations. Okay, so rotated about x-axis. Okay. All right, now if we look this small area here, what will happen there is we are going to have rotations, and we need to imagine what kind of solid that is going to be the result of the rotation. So this is the height difference between the first curve and the second curve. Okay, if we made the rotations, we will have this the disk. Okay, we will have the disk that is so if we draw like this, the black one there, so it's having a hole. Okay, so the disk is not a full solid, but it has some hole, right? Okay. Now if we take the radius, so we need to identify the radius. Previously in the area, if you have these two different equations, we can simply just take the difference on the height, right? The difference on the height, or the difference between the curves, the top minus the bottom, right? So this, in this case, this will be y1 minus y2, or x minus x squared, and then we can put in the integrations. But be careful in the volume. Uh, the difference should be the difference in area, okay? Or we need to not calculating the radius directly, so we need to exchange with the area of the circle. Okay, so it will be better if we write let's say this is the r maybe r1, and this will be r2. Okay, so the area will be, if we write directly, this is area is pi x squared, and then minus pi x squared squared. Okay, or we can write directly x squared minus x4 and then multiply with pi. Okay, we can write these integrations. Okay, oh, I forgot to mention the intersection. Okay, let me write the intersections. That is, we can have these equations, and we know that the intersection will be 0 and 1, right? Okay, so we can evaluate the volume from 0 to 1, and then we write the whole thing. Okay, and this will be our volume, and we can write the integration will be x cubed over 3x5 with over 5 from 0 to 1. Okay, or we can compute this, become 2 over 15 pi. Okay, let me give you another view on how we are going to use this method. Okay, let me give you another example. Okay, find the volume of solid. Okay, um, it was obtained by rotating let me check first. Okay, I think we can do it. Okay, okay, rotating the region on previous example. So the example that we have done before, which is the y equal x and y equal x squared, same curve, same intersections, right? And so we obtain this the solid by rotating the region about the line x equal -1. So it's not x-axis or y-axis, but another line. Okay, we can also try to solve this problem. Okay, let me draw the curves. Okay, let's look on what is happening here and what's the difference with the previous example. Okay, let's see. Let me draw the curve with the green color. This is the x squared. Okay, let me measure the left and right symmetry. Okay, I think this is quite good. And this will be the y equal x. Okay, I think it looks okay. Let me move to the right because I think we need to rotate to the x equal -1. So we need to make it longer to the left. Okay, let's take the -1 here. Okay, let's erase this part first, and then let's make a line that is x equal -1. And okay, we can try to look on this particular rectangle in the region, okay, the region area that we are going to rotate. Okay, and we are having another disk, right, with the hole. Okay, so this will be the shadow part. If you imagine, this is going to rotate it, okay, with the center of the line of x equal -1. Imagine it's being rotated through that line. And let me draw what is the disk. Okay, so this will be the illustration of the disk. Okay, we have a quite large hole. Okay, so we can check the radius. Okay, we have this radius here. Okay, let's say this is R2 and R1. Oh, sorry. Before I write R1, R2, but it depends on your preference, which one you are going to use, R1 and R2. The idea is you need to have, okay, the area, okay, of the circle, and now we have the function of y, right, because we are rotating through a line of x, so we need to have function of y, and we can write as the radius as outer radius and then squared, and then minus the inner radius and then squared. Okay, I think this will be better understanding. Okay, you can take R1, R2 in any way you want, as long as the definition is outer radius minus inner radius. Okay, okay, so you have the functions now. You need to change all the functions into function of y. Okay, so x squared become x equal square root of y, and then x equal y, it's just x equal y. So we can input into our equations here. All right, so okay, we write pi and then square root of y plus 1, okay, plus 1, and then write pi, and then this is x plus 1, right, x plus 1, because you have additional distance from the y-axis to the -1, right? So it's plus 1, okay? So you can have the integral from 0 to 1, or if we remember the intersections from the previous example, we can also write down y equals square root of y, which is we will get the results 0 and 1, okay? So we can write the volume, or in this case our area, and then dy. Okay, let me write in the bottom here. So integral from 0 to 1, and then 1 plus a square root of y. Okay, let me move to the right and then write the constant pi first. Okay, and then this is squared, okay, minus, we can write the y plus 1 squared, and then the whole thing, don't forget to multiply with dy. Okay, now this is the integration. I think you can expand the integrations, okay, you can expand it, and then one by one you can write down the results, and then input 1 and then input 0, and then you can compute the final result, and I think you can do it. This is not really difficult. So the difficult part on this kind of integration is to identify the radius, okay, to identify the radius, to imagine how the curve looks like, and the computations usually not that difficult, okay.